Hello, in this video we're going to talk about heat capacity. So, what is heat capacity? Heat capacity is the ability of a substance to take up energy in the form of heat. And so we have a number of different ways to describe this, and broadly we call all of them heat capacity, kind of as a general term. And then we have three different ways to define this. So we can define it as heat capacity, which is the amount of heat required to raise the temperature of any given substance by 1 Kelvin or 1 degree C. Remember, the Kelvin scale and the Celsius scale are identical except that their 0 point is shifted, so a change in 1 degree Kelvin is the same as a change in 1 degree Celsius. So heat capacity tells you how much heat needs to be absorbed to heat up your sample by 1 degree Celsius. And this depends on how much sample you have. If you have twice the sample, it requires twice the heat to raise the temperature, things like that. Now, at constant pressure, your heat capacity is equal to the heat divided by temperature, because this is the heat required to raise the temperature by 1 degree C. And then at constant pressure, heat is equal to enthalpy. So you can write this as an equation that heat at constant pressure equals delta H equals heat capacity times the change in temperature. And change in temperature is how we typically define it, final minus initial. Okay, so that's one way to define heat capacity. Another way to define heat capacity is the heat capacity per mole of substance. And so the units on this are joules per mole Kelvin. So you can say the molar heat capacity, which is capital C, is the heat capacity, lowercase c, divided by the number of moles, so heat capacity per mole of substance. And so the heat absorbed or released by a sample, which is delta H at constant pressure, is equal to the number of moles times the molar heat capacity times delta T. And so this is nice because this is independent of the mass of the sample, so you can list this in a book per se, and you could say here's the molar heat capacity for a given substance, and then you can use that number in a number of different applications. Now, probably the most useful way to describe heat capacity is to use the specific heat, which is the heat capacity per gram of substance. This is nice because you don't need to do any grams per mole conversions when you're working on this. And so the specific heat, which is lowercase c subscript sp for specific, is the heat capacity divided by the mass of the sample. So this m here means mass. And so your heat emitted or absorbed by your reaction, which is equal to the enthalpy change at constant pressure, is then mass times specific heat times the change in temperature. And so this is the equation we tend to use most often, just because it's experimentally and mathematically simpler. But you can use any of these three versions of the heat capacity equation, or molar heat capacity, or specific heat, as long as you keep the units straight and use the appropriate pieces with it. If you're going to use the molar heat capacity, you need to put the number of moles with it. If you're going to use the specific heat, you need to put the mass with it. And if you're going to use just the straight heat capacity, you need to figure out what that is for your given quantity of substance. Now on the exam info sheet, you'll be given this line, where the heat at constant pressure, which is equal to enthalpy, is equal to the heat capacity times the change in temperature, or the molar heat capacity times the number of moles times the change in temperature, or the specific heat times the mass times the change in temperature. And so to keep these straight, let the units be your guide. If you have a value for something related to heat capacity and it has grams in it, you need to multiply it by grams. So you're using this equation here. If this value contains something about moles, use the one with moles. And if this value is just joules per Kelvin, then just multiply it by delta T and you're set. Now, your book likes to use molar heat capacities, and so here's a table of molar heat capacities for various substances. Now, most of these values are somewhere between 20 and maybe 50 joules per mole Kelvin. However, liquid water over here is our outlier. This has a very high heat capacity, 75.3 joules per mole Kelvin. And so we see the effect of this in lots of different ways. When you're, say, at the beach, it might be a little cooler because the ocean has a very high heat capacity. Climates next to an ocean are much different than climates inland because the body of water plays a large role in regulating the heat. So the ocean will absorb a bunch of heat during the day and then release that heat at night and overall have a moderating influence on the weather of the area. Okay, so let's do this problem two different ways. First, we'll do it with the molar heat capacity, the capital C subscript P. And so when we use molar heat capacity, first we need to know the number of moles that we're working with. So here we convert the iron into moles of iron. So here's the equation we need to use. And then the first thing we put in is the number of moles. And then we put in the molar heat capacity with units of joules per mole Kelvin. And then we put in the change in temperature. And so let's think about units here. So the moles cancel, that's easy. Now the kelvins and the Celsius cancel. They don't normally, but when you're looking at a change, remember that a change in degrees C is the same as a change in Kelvin. So you can get away with doing this subtraction in Celsius and then saying it's the same as Kelvin and canceling out the Kelvin. So this only works when you're dealing with changes in temperature. And so if that worries you, feel free to convert it to Kelvin and do your subtraction in Kelvin. That's totally fine. Okay, so we get 17,000 joules, and it's going to be easiest to put this into kilojoules because then that gives us 17 kilojoules and allows us to show off the sig figs a lot easier. And so for sig figs, our change in temperature is going to give us 74 Kelvin is our change, and that has 2 sig figs. Great, so this is how you would use molar heat capacity to do this. But it's going to be easier if we use the specific heat capacity, which is in grams. So let's show how to do that. Okay, so now let's try this same process using the specific heat. And so when we do this, we're going to use this form of the equation, mc delta T, and then we start with 523 grams as the mass, and then you put in the specific heat in joules per gram degree Celsius, or your source may say joules per gram Kelvin, either one will work. And then you have your delta T, final minus initial. Now, the grams cancel, that's straightforward. The Celsius cancels, that's straightforward, and you're left with joules. And then now, this is equal to 17,000 joules, and then if we convert it to kilojoules, we get the same 17 kilojoules that we got before. So the specific heat's easier to use experimentally because it's already in terms of mass, and usually you're dealing with mass somehow when you're doing this in the lab. But really, the specific heat versus the molar heat capacity, they're only different by a factor of the molar mass of the compound. And the same between the grams and the moles, are only different between the molar mass. And so you can convert from one to the other no problem just using the molar mass. Okay, so that's how we deal with heat absorbed or released by an object. But why would we want to know this? Well, the primary application here is dealing with thermal transfer. So this is when you have heat transferred from one object to another. Then this has many applications in both scientific practice and the real world. So in scientific practice, you can use how much heat is transferred to identify enthalpy changes in a reaction or identify heat capacity of metals and measure that. In the real world, for instance, you could use this idea of thermal transfer to see how hot some object's going to get, which you may want to know if you're doing some engineering or considering materials or something like that. So it's a really important concept here. So what is this? So the definition of thermal transfer is when you put two substances together that have different temperatures, they will result in heat transfer between the substances until the combined system obtains a uniform temperature. So an example here is if you take a hot rock and put it in a glass of water, you're going to heat up the water and the rock will cool down until you reach some constant temperature where the rock and the water are the same temperature. The rock is colder than it was before, the water is hotter than it was before, and then you have reached a thermal equilibrium here. And so that's what this diagram's trying to show, that the hot object and the cold object will exchange the heat. And so the heat always flows from the hot object to the cold object. If you can think of heat as an object that flows, which people usually do conceptualize it this way. and so you can just go with it because it makes sense. So heat flows from the hot object to the cold object to equalize the temperatures between the two. So then, thinking about this with the equations, when you have heat flow, the heat is lost from the object at a high temperature and gained by the object at the low temperature. And now you can write the equations this way, that the heat lost plus the heat gained is equal to 0. So perhaps a better way to phrase this is that the heat lost by the object at a higher temperature is equal in magnitude but opposite in sign from the heat gained by the object at a lower temperature. So in other words, these two things are the same number, they're just different by the negative sign here, which makes sense. And I put the negative sign on purpose on the hotter object because normally we think that the hotter object losing heat is negative, and then that's gained, which is positive, by the object at a lower temperature. So this heat is just transferred from one side to the other, and it's just different by this negative sign. Now you can take this equation I just wrote and then add Q high to both sides, and then you get this equation over here where it's just equal to 0. Then, from here, you can go about and use the various equations we have for Q. I'll just talk about the one we tend to use most often. Q is equal to the mass times the specific heat times the change in temperature. So you can just plug this in. Here's the mass of the hot object, its specific heat, the final temperature, the initial temperature that the hot object started at, and then you have the mass, the specific heat of the lower temperature object, its final temperature, and then the initial temperature of the lower object, and this is all equal to 0. Now when you do this, the final temperatures are going to be the same for both objects because they're in thermal contact and they reach an equilibrium temperature. But the high temperature and the low temperature where they start are of course going to be different. And you can use this equation, if you know all of these variables except one, you can solve for the one that's not there. So you can find unknown heat capacities, you can find unknown masses, things like that. And this is the heart of something we call calorimetry. And so this is what we talk about in subsequent videos, where you can use this exact technique to then find out useful information. And so we'll talk about calorimetry in a future video, but at the moment, that's all we have. Thanks for watching.